Hey everybody, so this is just going to be number 15 and number 16 on your homework on the linear motion guided reading because it's not that intuitive and it's not found in your book because I want to see how you think the motion is going to look like what it's going to look like with our velocity vectors and with our coordinate systems. Okay, so let's just read over 15. So in physics, the term acceleration works in both positive and negative directions. So if I was going in the positive direction and speeding up, it would just be called acceleration, right? But if I needed to slow down, it would be called deceleration. If my positive coordinate system was to the right and my negative coordinate system was to the left, described with a picture and words, the acceleration vector if the car is traveling and speeding up and if the car is braking. Okay, so I'm not asking you to draw a car unless you want to, because that would be pretty cool. Like if you're really good at drawing, feel free, but I am not, as you will find throughout the year. So I am just going to start with a little dot, and I am going to call my dot car. Okay, so let's just start with the positive x direction. So let's just visualize an x-axis, and the positive x direction is going to be here, towards the right. Okay, and let's call this position right here 0, 0. So I haven't moved anywhere and no time has gone by. Okay, but let's just call this position 1 second. So I started moving and I stop at that 1 second mark. So I'll just call this velocity 1. It's a vector quantity, so I'm going to put a little hat on it. Okay, and let's say at 2 seconds I'm here. Right there. Vector 2. And let's say at 3 seconds I'm all the way down here. Vector 3. Okay, so those are my velocity vectors. Okay, and as we can see, ooh, sorry, I just bumped into my desk. As we can see from our time, so that's 1 second, 2 seconds, and 3 seconds, we are accelerating. Why? Because there is a change in velocity over time. And if you cannot see the change, you can see it right here, right? We can pictorially see that change because the arrows are getting bigger with each second. So there is a change in velocity over time. So that's all I'm really asking you to do for this one, for the positive x. Now let's look at the negative x and deceleration. So let's just call this over here negative x. And let's call over here our 0, 0 position. So we haven't moved anywhere and we're at 0 seconds. Okay, so let's just say that our velocity was really big to start with on that first second. So we're going like 0 to 60, okay? So we'll call this velocity 1 and that vector hat. But then we start noticing that there's an end of the track. So we have to start stepping on that brake. So the vector gets a little bit smaller each second. So this would be second 2. So we'll call this 2. And a little bit smaller again. So we'll call this velocity 3. That's 3 seconds. And then we start really decelerating. Okay. So again, we can see that we are decelerating. How do we know? Because our change in velocity is getting smaller with each second. Okay, so we can pictorially see that our car at 1 second is going from like 0 to 60, right? And then we're like, oh no, we have to start braking, pull that parachute, right? Because there is a wall ahead of us and we definitely don't want to crash into it. So as we pull that parachute, we start slowing down so that each second our velocity change is getting a little bit less each time. Okay, so that's all I'm really asking you to do again. If you can't see it right now, that is okay. Just do your best. Again, I agree on effort and completion, not really on accuracy because it's homework. You're still learning. It's all about practicing. Okay, so let's look at number 16. So a car is traveling in a straight line and steadily increases its speed each second. Okay, so we can see that this change in velocity, there is going to be a change in velocity, which means this car is accelerating. So first from 35 to 40 kilometers per hour, then from 40 to 45 kilometers per hour, then from 45 to 50 kilometers per hour. What is its acceleration? And draw a picture if it will help. Okay, and show all work. So I love pictures. I think they're great. So I am going to draw a picture and I think you should too. Okay, I'm pretty sure it says it on your homework to do so. So again, we just start with that little dot. We call it car. Yay. Okay, we put in our coordinate axis. So this will be negative x. This will be positive x. So if our car is starting from the 0, 0 position and going to the right, it's going to be a positive change. If it's going to the left, it's going to be a negative change. All right, so first from 35 to 40 kilometers per hour. So I'm just going to start right here. I'm going to call this my 0, 0 position. So we went from 35 to 40 kilometers per hour. So I'm just going to call this right here, just like before, velocity 1. And this is going to be 35 to 40 kilometers per hour. Okay. Oh, and now we can see again, there's an increase in speed. Okay, let me just make that a little bit more clear. Kind of looks like the same, so I want to make sure that we know that it is accelerating. Here we go. So then we accelerated again from 40 to 45. And let's not make that look like a minus sign. Yeah. So we'll call that kilometers per hour. And we will call this velocity 2. And then again, we accelerate. So we accelerate from 45 to 50. Okay, and we'll call that velocity 3. Okay, so as we can see, we are moving in the positive x direction and we are changing our velocity every second. So we can call these seconds, right? So we can call this 1 second, 2 seconds, and 3 seconds. Or it might be easier in this case scenario to call them hours, but it's okay. We'll make it work. So we want to find the change in velocity per time. So yeah, let's just call these hours. Even though it's probably not accurate to do so, it's going to be easier for our problem and it's fine. I just want to see if you understand what acceleration is actually indicating. Okay, so let's just call these hours. So acceleration equals the change in velocity over time, over a given amount of time. Okay, so what does delta V mean? Velocity final minus velocity initial over time. So what would our acceleration for 1 be? So let's just look at vector 1, right? So velocity 1, we have a final position of 40, and we go to 35, and it is all over 1 hour. Sweet. So let's write it out again. So we are left with 5 kilometers per hour per 1 hour, or 5 kilometers per hour squared. And we know it's squared because it's hour per hour. So, and our acceleration is measured in our base unit meters and our other base unit seconds squared. Okay, so it's measured in meters per second squared. Okay, so Let's look at number 2 and see if anything changes. Well, our final velocity for number 2 is 45, and our initial velocity for number 2 is 40, and the time is 2 seconds. So let's see if it changes. And I know what you're probably thinking. Well, Miss Brennan, if I throw in the time, it's going to be 2 seconds. But you have to indicate your change in time. So you went from 2 seconds as your final, and you started from 1 second. So you have to subtract that. I'm sorry, I've been saying seconds, hours. So you started from 1 hour and you went to 2 hours. So what is that a change in? 1 hour. So let's see that out. Let's not get confused here. So I still have that image. Yes, okay. Let's see it out, right? So let's just call this acceleration 2. Okay, acceleration 2. That is equal to the change in velocity over time. But it can also be indicated as the change in time. And here's why. Because final velocity minus initial velocity is happening at different times. We have to recognize that even though we started at 2 hours minus 1 hour, because we're not starting from that 0 position, we're starting from that 1 hour position and then accelerating. So right here, again, we have 45 kilometers per hour minus 40 kilometers per hour all over 1 hour. So we are left with 5 kilometers per hour squared. Okay, so again, we know it is positive because we are moving in the positive x direction, and we know that it has to be a change in time because we're not starting from that 0 position anymore. We're starting from that 1 hour position. So let's look at it for number 3. Again, we're not starting from that 0 position, we're starting from that 2 hour position. Okay, so we have a delta V over T, and that time can be your delta time. Why? Because it all depends on where you're starting from. So we have a change in V over your change in time for this scenario. So we went from 3 hours and 2 hours, okay? So 50 kilometers per hour minus 45 kilometers per hour. 3 minus 2 is 1. So we recognize that we are accelerating the same amount each time. So we have a constant acceleration, but it's happening over the same amount of time, which is great, but it's changing our velocity. So we're going to look at this in our lab. You are going to see this, and it's going to be probably more easier to understand once we start seeing it in different graphs. So I hope this helped. If it didn't, let me know, and I can give you another example to try and show this to you. Again, it's very challenging, and I understand that. So if you need some help, again, please reach out to me, and I will see you all soon. Bye.